I'm not sure how to get here to the to the settings. Okay. So we start the Gaia working group meeting. By the way, I think I recommend you to maybe come to the first rows. I think it would be more easy to have a conversation than if you sit in the back. But feel free. I mean, it's just.
And folks, can you make sure you sign in the blue sheets that are circulating, because we have to submit that to the Secretariat later. Thank you.
Do they have not takers? Or?
And thank you very much for coming to Gaia. You all deserve an award for finding the room in and of itself. This is the Global Access to the Internet for All, and I was talking to John Crowcroft, who's in the back from Cambridge University. He's the one that came up with the name, so thanks, John, for naming us. And Arjuna, who used to be the co-chair of Gaia and who deserves an enormous amount of credit for getting the group off the ground and for rallying people around the world to talk about critical access issues. And one of those people that he's been rallying is Leandro Navarro, and I'll let Leandro introduce himself.
Hi, I'm Leandro. I'm associate professor at the Universitat Politècnica de Catalunya, which is a university in Barcelona. And I'm also involved in several activities with ISOC, with the European Commission, and I'm also executive board member of the Association for Progressive Communications. So it's a pleasure to be in this group. I've was a member since more or less the beginning, and I hope we can contribute to make it even more successful.
Excellent. What we'll do is the agenda is online, and I'm going to pull that up now. And what we've been doing over the last 2 to 3 meetings is bringing people in who are practitioners in the field, researchers, obviously, because we're under the IETF, who are doing work on whether it's network flows, trace routes to take a look at where traffic is going or isn't. Everybody from the African projects to AMO, Gareth is here who's working on that. The Internet Society is doing some trace route work on traffic flows in Africa as well. But as Leandro said, one of our big focuses has been on community networks, and that's something that Internet Society, APC, different university researchers, and people in the field are very interested in. And it was part of the plenary yesterday, where we're seeing places where connectivity isn't. And because of the confluence of cheaper technology, people connecting to each other, seeing each other at meetings, there's this wealth of knowledge that's transiting across borders. Through meetings like this, meetings that ISOC or APC may pull together. Some of us, Steve Song and I, were up in Geneva at the beginning of this week for something called the World Summit on the Information Society Forum. Some people think it's a talk shop, but actually what we're trying to do is bring more technologists to these places where people talk so that we can start to marry and merge the talking and the policy and the regulation with the reality, right? Sometimes you can't get a project going because there's a licensing issue. Small startup networks in regions with not a lot of capital, but a lot of human effort, they can't afford a year to get a license, right? Or an authorization. So we've been trying to work with people to encourage the idea of giving these small networks a break, helping them out by giving them social purpose or experimental licenses to get off the ground with spectrum, or changing universal service. There are millions of dollars sitting in banks around the world that are supposed to help rural, remote, and underserved projects. You can't get them started. So governments are beginning to realize that there's an opportunity to work with technologists, researchers, universities, people like all of us, to try and promote connectivity. Because some of the bigger companies right now do not see a return on investment in going in some of those smaller places. That's their model, but we've seen models that work at the local level. And some people here are here to tell you about that. Sarantaporo, a project in Greece, very interesting project. Vasilis is here to talk about that. So I will stop talking. Anything else from your side? No?
Yeah, maybe one comment is that depending on the time we have left at the end, we should probably try to discuss about how we move forward, and especially as Jen said, I mean, one of the objectives is to highlight good experiences, and maybe if we discuss about how to make them more visible, how to give them the opportunity to be known through the means of the IETF documents, that would be very useful.
And if you're a first-time attendee, we've got to show you the note well. It's part of the drill of the checklist of things I'm supposed to say. So one, make sure you fill out the blue sheets if you haven't signed up. Sign up. This note well, I'm going to go through. Just a reminder of IETF policies in effect, various topics, patents, code of conduct. It's meant to point you in the right direction. Exceptions may apply. There's a patent policy definition. And you can see the website if you want to take a look. So as a reminder, by participating in the IETF, you agree to follow IETF processes and policies. If you're aware that any IETF contribution is covered by patents or patent applications that are owned or controlled by you or your sponsor, you must disclose that fact or not participate in a discussion. As a participant in or attendee to any IETF activity, you acknowledge that written audio, video, and photographic records of meetings may be made public. Given the European rules on GDPR also, if you're in this room, does anyone have a red lanyard on? You do. Okay. So I'm going to have to ask you, do you mind that this is being recorded? Because by being in this room, okay. Thank you. Wonderful. There's some other people too, so I'm not signaling anyone out, but I want to be very cognizant that we're aware that if you see somebody with a lanyard that's orange or red, please don't photograph them without asking them for their permission. Also, this is being live streamed, so just know that. And if you're comfortable, great. I know your face can be considered PII, right? So as a participant, personal information you provide to the IETF will be handled in accordance with the IETF privacy statement. As a participant or attendee, you agree to work respectfully with other participants, and please contact the Ombudsstein, that's a weird word, if you have questions or concerns about this. Anyway, there's more information at this site if you have questions. So back to the agenda. We have Dirk Trossen who's up first. And Dirk, you'll be speaking from this microphone and we're going to pull up your presentation. And thank you to everybody that expressed interest in coming, and we're so happy that you're here. And if you have presentations for the folks on the live stream and you weren't able to meet the queue for presentations here, we're happy to load your presentations to the website so that others can see them. So over to you, Dirk.
Good, thanks. So this is a small introduction into the field trial in the RIFE project that we are conducting at the moment still. The presentation is joined with Renan Krishna, who's done a lot of the legwork in our company, and Roger, who can't be, unfortunately, here from Goofy.net, who provided some of the slides at the end. Let me give you see the URL of the project here. So I don't have a partner slide at the moment, but and if you go to the website, you can see the partners involved, Cambridge University, Technical University in Munich, Alto, but I might miss a couple of Thales. Don't make me list them all. Just look at the website. It's an EU project that started in January 2015. It was meant to end by the end of last year, but we extended it by the end of January. We extended it by 2 months in order to conduct the field trial, which you will see in the following slides. So it's going to last until the end of next week. That's when the project is officially over. And I'll come to the next steps at the very end of the presentation. So I'll talk a bit about the objective, just one slide about what the project intended to do, at least for the field trial. There are a number of research activities in that project, but I've focused particularly on the ones that we were looking in the field trial. A bit about the architecture background, where this comes from, what we've done, What we actually deployed in the field, this is courtesy to Roger, who provided a lot of these slides of what's actually the boxes and bits and pieces that are deployed and also where they deployed, and then a few words on the next steps. So RIFE, a lot of these EU projects, in case you're not familiar with, have a short word and a long title. RIFE is the short word, and it stands for Architecture for Everybody. Now, whether or not we've done that remains to be seen, but definitely we wanted to utilize a new network architecture to provide better connectivity or internet connectivity for communities, for community networks, with better being a number of things, and the ones I've focused on here, which we try to address in the trial, is easy to deploy, meaning a software-based solution, relatively simple to manage, performance benefits for certain IP-based services, as well as enabling services that are otherwise hard to do, in particular if you have remote connectivity and you might have a constraint backhaul link that you might need to overcome. As an architecture background, this shows the system architecture that we've developed as part of this project and a accompanying project that we ran, the so-called Point project, which ran in parallel to RIFE. And there's a lot of overlap with respect to the actual architecture and the technical work. So these two projects collaborated. And what you see here is an edge IP architecture where we use standard IP devices, obviously like your home router, as well as your home devices that you use, all of them still IP-based. And we place the inside of the infrastructure. So in the cloud, you see three main components: a forwarding node, which in our case is the one that we deployed in the field trial, is an SDN switch, soft switch, an Open vSwitch. TM and RV are terms that come out of the information-centric networking research and stands for topology manager and rendezvous, because we use an ICN, information-centric networking abstraction, to realize the IP connectivity on top. It might sound a little bit strange, but it allows us to do things that are very difficult to do in a normal IP network. At the site, this way, at the site you see the border gateway, so we have normal internet connectivity to peering networks. And in the case of our field trial deployment, that's provided through Goofy.net. We use edge caching solutions to front load content, which then could be which then is consumed purely in the front haul network. That's our aspect that makes at least internet cheaper for some content services, but just front loading the content and making it available locally. And then we just peer to other networks. These other networks could be other community networks, or they are just what you commonly know as the normal internet. From an IP perspective, obviously the biggest requirement was that it must support the current internet. So anything you're really used to, and we used to run the demo. I think I actually pulled up slides of a Gaia presentation I gave about 2.5 years ago or so, and we actually ran the demo there, where we just open up a Wi-Fi access point, people could connect to it, and you were actually running over it. You don't see any difference because you just we noticed that most of what the people were doing is accessing Facebook, funny enough, when they went on the Wi-Fi access point. Probably that would be slightly different today, I don't know. So it must support the current internet. We hope, obviously, with better performance, and it addresses the affordability and QE aspects in the sense of that we can provide advantages over normal IP, and I come to this one in a bit. The foundations for other propositions that we've built throughout the projects, and one of these is the so-called surrogate. I have a separate slides on those. These are alternative service endpoints that are deployed within the network in order to either reduce latency or overall cost of the deployment. And this is all achieved through what we call the IP or HTTP over ICN solution that we've built in these two projects in RIFE and Point. We also were looking at new services, either by using native ICN in selected areas. We haven't done an awful lot of this. But you have, as you, this is actually a different picture. I'll replace it in this picture. But you also have, obviously, access to the actual ICN underlay that we are using, and therefore you can deploy native ICN services. The project just hasn't done that much on this because there's a totally separate ICN work that's currently ongoing in the community, but you could utilize this. Also DTN-based services. There's one particular form of an ICN. We have partners working on delay tolerant networking, and in the trial that is currently based on this architecture, we replaced temporarily for the last week, which should be next week, we're replacing actually the trial with a DTN-based trial, even though I think the last information I have is meant to run in parallel to this trial because we have some spare capacity. The deployment flexibility we wanted is, and this is kind of like a terminology we developed in the project together with Roger, is to allow us to go from really well-planned networks. These are not the networks we're really talking about. Well-planned means I have a relatively good flexibility and ability to actually place infrastructure. That's not always the case, right? We are more after well-connected, less well-planned, and this means when the community secures a place, that's probably where you put it. That might not be optimal. You might want to use the church tower, but you can't get to the church tower, so you just make do with whatever you're getting. So it's more this connectivity. Connected is the local connectivity we are using with directed Wi-Fi is relatively well connected. The connectivity itself is quite good. But again, it might be suboptimal from a planning perspective. We also were interested where the DTN deployments come in less well connected and very little planning, almost down to random encounters. And this is obviously where your fixed infrastructure is literally out of the window, and you're trying to make do with whatever connectivity that's currently available at any point in time. This is why we had the DTN angle in our trials as well. The surrogate placement, as I said, is we experimented in the very beginning very much with the edge caches, which are normal HTTP proxy caches, but they are pre-placed. They offer pre-placed content, and we replaced this with an idea of surrogate service endpoints. The difference there is it exposes the service under the fully qualified domain name of the regional service. So it isn't working in a proxy mode or in a portal mode. Thales, our satellite operators, has a solution that is portal-based, and therefore it is obviously exposed to the end user because you have to access content via a portal. In this case, we're really replicating the service endpoint in the front haul network, and the entire service is exposed under the original fully qualified domain name. That obviously requires that you have name authority to do that, which for selected services we have. This is the architecture we built. I won't go into too much detail, but the main message here is that the move was to really move from content retrieval, from pure caching, to entire service routing over ICN. So you really front haul the entire service endpoint into the front haul network under this name authority, and therefore both content as well as computation is front-loaded, and that reduces traffic obviously even more. So computation content, the latency is therefore one target, so we really want to make sure that not only your video asset is there, but anything that's around it in terms of computation is in the front whole network as well. Not that relevant for the community network because we haven't done it, but we push this in other deployments at the moment further, where we have a more advanced infrastructure that is, for instance, network function virtualization based. So the new platform that we have built from in the digital side deploys entirely through NFV, and we demonstrated this year, where you can boot a pristine infrastructure at municipal scale within about 10 minutes. And you have your entire routing infrastructure deployed, and you can run your service. That's up. But again, all of the infrastructure is essentially the same we deployed in the community network. It's slightly more powerful. They're normal x86 white boxes. It's just in the municipal, and that's a deployment we have in Bristol. Those are URACs, so they're actually really powerful Dell servers, while the community networks we deployed are slightly more resource constrained, but the compute architecture is the same. Right? So therefore, we see this still as relatively interesting. Once you have advances in the compute infrastructure, you can easily run those in community networks, maybe in a few years' time. Right? Good. What have we actually deployed? So the actual field trial takes place in Tarragona. That's not the city, that's the community, which is in Catalonia. It's a production network. So it's actually, they're real people. Part of the trial, which is also explains a little bit our delay. If you fiddle with people's real internet, you want to make sure you're not screwing this up. So that's a bit of the issue. It's a production network, and people are actually really accessing at the same time. The links are technology. Link technology is Wi-Fi, so there is directed Wi-Fi between the actual so-called supernodes. There are 6 supernodes in the infrastructure, and the access points are 15 access points with more than 40 households that are being served.
Julius Krabachuk, what's the scale of the map, roughly?
These are a few kilometers between, sometimes several hundred meters or kilometers between the supernodes. It provides a real-world environment. Some of the things I said that complicated things was because it is a trial, and I come to this, you see this in the setup, and I'll show one of the boxes in a second, is because we have parallel connectivity. We do, because it's a field trial, it's experimental software, we have normal IP routing software in parallel running to the IP over ICN one, and that explains some of the complexity in the setup we're having. We can switch immediately between our experimental trial and normal off-the-shelf IPs one, and that increases the complexity of the configuration. That's one of the reasons why we had a delay in our trial. There's also parallel, so the way the staging was, it should be actually the other way around, is because we stage everything in the lab. So we start in the lab first, and then we go in the trial, where we take a very simple 3 supernode lab model, test everything, and we run test suites, and if it's working, it's being deployed in the actual village. So we've also made to make sure that we are not messing too much with people. So this is the router boards we are using in the trial. Up on this side are the point-to-point links to other supernodes. So these are the distant point-to-point links, and then the actual point-to-point links to the access points. And we have 2 models of deployment. One is where the access points are IP devices, or where the access points are IP over ICN devices. It's a different form of deployment which has different benefits, which is why we tried both of them. The reason why you see always everything in threes is because we have a management VLAN setup, and we have an IP only VLAN setup, as well as an IP over ICN. That's the parallel setup we just have to provide in order to not mess with people. We switch in a few seconds from a faulty IP over ICN. If our trial fails, we're switching over in a couple of seconds onto the normal IP network. So the households don't really quite notice something, and then we repair the issue and we're switching them back. Right? You can get rid of all of that if you, and I come to this in the next steps, if your software is stable enough, you just remove all of this nonsense. Right? This is really trial stuff, and that's the reason why, this took some time to do. Yeah. Off at is the general compute devices. So these are, as a normal commercial super router boards, and the actual compute infrastructure are embedded AMD devices with 4 cores. As a normal x86 infrastructure on which we are running the software directly. Yeah, I won't go into these ones. So it's a dual stack backbone, IP or ICN, depending on our mode. The ICN backbone is purely L2. So you run everything straight on L2, and I can give you more on this, and that takes about 20 minutes longer to explain that. The households are attachable either at the AP level, and that means that every household is spawning off an actual IP, or each household has an AP actually built in. These are the 2 different modes I mentioned before. The core components are always reachable via IP management connectivity, just in order to log in and maintain the software. So what are the next steps that we are really looking into? Now, this has all turned out to be much more complicated, and the reason for that is if you deploy this in real life of actual real communities, it does take significantly longer. So the trials have been cut short quite significantly, and we are currently in discussions with the community that goes to a comment that Jane made before, to actually continue and help them to get off the ground with an extension of the trial. This would run after the project. So the project finishes next week, and we made a commitment to the community to continue the trial for another year to gain insights, and also to switch the software. That goes back to the comment I made before. We re-engineered the software. So InterDigital has a new software solution, and we would like to replace the original software with a new software, which then also allows us to simplify all of the setup, because we have significantly higher trust in our new software than we had in the original software. And that kind of makes the whole VLAN setup significantly better. So it has higher stability, better security. There are some security issues with the current setup because it's experimental. So if you would really switch this to production, you would get rid of some of the security things very significantly. We also want to perform planned experiments. Some of the benefits that I was talking about before, they do require some planning with the community. For instance, some of the benefits that we have is in the community here likes watching football events. I'm not telling you obviously which club it is, but you can imagine which club they like watching really live. And that's a very, very particularly expensive service, because it goes via the peering link, which is expensive. And it's usually watched via HLS technologies, meaning on HTTP level, it's unicast, and therefore it puts even more strain on the peering link, because 40 households, 40 streams, right? And we can cut this down. We demonstrated this in separate trials that were done in the sister project. And this is an experiment we are trying to run with the community next year, to have these type of community and kind of viewing experiences significantly cheaper than they are today. Good, thank you very much.
Wow. So each speaker has 10 minutes, and we've got about 2 for Q&A, but obviously they'll be around. But does anyone have a question for Dirk? Yeah, please go to the microphone. There are people remotely participating, and so you've got to speak into the mics.
Hello, Andres from University of Cambridge. Dirk, you mentioned that you're switching from ICN to IP. So what are the specific cases in which you're doing that? And what are the implications of that switching?
The cases are purely failure. So we have watchdogs in all of the software components, and we switch over in failure cases. I said it takes a couple of seconds to do that. And that's mainly, well, if one of our software components, as you know, some of them have a couple of issues, and we switch over. The software is not set up that we can experiment in parallel. We had run a trial in another project last year. We actually had parallel setups. That's even more expensive to do. And in this case, we actually bounced some people on an IP network, some people on an IP or ICN, and we ran experiments in parallel, and they had no idea. It was randomly done. And we tossed a coin, and then we looked in the database on which network they were, and we asked them questions. That's quite interesting, but that's very complex to set up. And at this scale, we didn't want to do that. So this is really failover only.
Excellent. And we have a question, a remote person in Mexico with Luis Martinez, who runs a network there. I'm going to try and bring you in, Luis. Give me 1 sec. Go now. You can ask your question. So that's not working, but Luis had sent me a note saying he wanted to know how the simulation compares to reality.
Well, this is reality. We have actually done a number of simulations that scales this significantly up. So the community is a decent size. So even here, we would expect there's still one of the project deliverables is due that actually performs a socioeconomic analysis on some of the, for instance, the multicast benefits that we are talking about. And the scale is similar to the trial community. If you scale this even more up, we've done this in the sister project, where we perform simulations of significantly higher scale.
Awesome. And Luis, you might want to put that out on the Gaia list to ask the question too, and Dirk could respond on the list as well. So we have about 30 seconds.
John Brewer, NSRC. This sounded a lot like what Fraunhofer are doing with their Wyback project, which they've contributed to Facebook's Telecom Infra project. How similar, and are you working on the same problems from different angles?
So it's similar so the caching work is very similar. When actually Avanti was part of the work as well. Avanti, it was one of the partners I forgot to mention, by the way, before. So Avanti it comes from the satellite side. And the edge caching I was talking about before is very similar. So they brought their original edge caching solution. We improved on the edge caching solution, but then also went further by actually looking into entire service placement. So not just content, but the entire service is pre-placed. So it takes it on. We also have more front haul work because this project actually was mainly focusing on caching part, and it was using a standard front haul network. We also look specifically with these IP over ICN solutions at the improvement of the front haul delivery in the community network.
Excellent. Thank you very much. This was fabulous, and we appreciate you participating.
Thank you very much.
And Dirk's on the list, so if people have more questions, and he's also here for today, yeah?
Yeah.
Okay.
Yes, absolutely.
Excellent. Thank you. So, next up is Connecting the Edges, the U-Mobile project. Sotiris, are you here? Excellent. So each speaker has 10 minutes with 2 for Q&A. And over to you.
Hello, this is my first time in the Gaia meeting, and this is a vivid community. I'm Sotiris Diamadopoulos, coming from Xanthi. I'm with the Athena Research Center and Innovation Center, and I'm going to present you actually our research directions in the U-Mobile project, which started 3 years ago and is going to be concluded in 2 months from now, 1 month from now. Actually, the main objectives of the project were to develop a consolidated information-centric opportunistic and delay-tolerant communication platform. The basic idea was to integrate information-centered networking and delay-tolerant networking, but finally this led to multiple research directions that I'm going to present. Another objective was to provide an architectural support for the network edge, drive the internet towards a communication platform for universal coverage, focusing on remote areas or disconnected areas, and drive along the way new application models and services. From a high-level perspective, the idea is that the mobile domain starts where the internet domain would end, and our focus was actually dual. The one was to create a networking platform that will facilitate communications within the community without the need to communicate with some centralized services. And there are some mechanisms that I'm going to present later. The other idea was to create the infrastructure again to move services closer to the users when this is necessary. So what we've done was to try to exploit all communication opportunities, try to incorporate DTN in order to support disruptive communications, actually supporting devices that may be disconnected in space and in time, facilitate user and service mobility, create a mechanism in order to support application data and computation sharing, and create a routing mechanism for opportunistic networks, which is based on social-based routing, actually, social-based metrics. The mobile architecture is depicted here. The blue boxes are native NDN, named data networking mechanisms, such as the NDN forwarding, the faces, which are the interfaces that the NDN uses in order to talk to the other protocols. The red boxes are what we have done in the mobile project. I'm going to go through some of these here. In terms of forwarding, we have created a TTN interface for the NDN platform to provide reachability and reliability when necessary. We have done this protocol, which is called opportunistic off-path content discovery, which can be used in a remote decentralized network where a new table, this is NDN terminology, is used in order to find data which is off-path, let's say, not exactly on the route of on the central nodes of the network, and name-based replication priorities, where there is some prioritization mainly used for disaster scenarios, where some data, some interests, and some content is being forwarded based on the name and priorities, time to live, and the geographic area of dissemination. In terms of routing, we have worked on this opportunistic part of the NDN platform. These are some modifications on the basic NDN platform in order to facilitate communications in opportunistic scenarios where connectivity may not be so good. We are working now on the double protocol, which is a draft in the IETF community. with our partners in Cope Labs, Portugal. Also, we are, with regards to the contextualization, we are employing social metrics in order to improve data dissemination. This is work from our partners again in Portugal in Addison. What's root? No, Cope Labs and Inception. Thank you. No. And this contextualization manager is the one that can pass information not only to the routing mechanism but also to any other application that would need this information. Now this sounds like Cambridge Analytica. Now, regarding the northbound APIs, what we provide to applications, we have the keyword-based mobile application sharing. This is the mechanism, an API that will allows applications to share their data, so that if you are in a disconnected environment and you have access only to an access point, or don't have even access to an access point but only access to other nodes, you can use an application which must be compatible with the other applications to exchange application and computation data. Let me see. Okay. Regarding edge service deployment, we have created with Addison, we will present some results on the following presentation. We have created a quality of service mechanism that can migrate a service from the central part of the network towards a remote area, and maybe it can be affected area or anything, in case this kind of service is needed in this area. We're going to see some results later on. And finishing my presentation, this would be the mobile platform as a whole, meaning that we have an area which could be the mobile area with hotspots, along with the hotspots, or in this area we could have also mobile and user service, which is based on a smartphone, which is actually located in a smartphone, where this allows communication between end users, and also between the end users and the mobile area. And we also are close to the base network through the mobile service manager, which can move service, as we said, towards the unaffected area. That was my presentation.
Brilliant. Okay, because you were spot on, we have 3 minutes. And so who has questions for Sotiris? The microphone's here, up at the front. And if you can make them as succinct as possible so we can get in as many as possible.
Sure.
Go ahead.
I'm Julius Krabachak. I have 2 questions. The first one is, does it work? Never told us about the results.
Addison is going to.
Oh, okay, perfect. And the second question is, what you are speaking about node-to-node communication without an access point. What are the link layers that work? You mentioned Wi-Fi. You were speaking about node-to-node communication without going through an access point.
Yeah.
And you mentioned Wi-Fi direct. Are you using other?
It was written somewhere. It's Wi-Fi direct.
That's the only link layer that you use.
Yes.
So we need to make sure we're speaking into microphones. Can you, yeah, go ahead. Just because there's a remote participation and we want them to hear it, and it's being recorded.
What we built it here is like NDA we mentioned about here is like overlay. So you can plug
Microphone.
You can plug into any physical layer, layer 2. Like for example, in our deployment, we also plug our prototype to the Wi-Fi access points as well. So it can run over the Wi-Fi or can run over Ethernet or Wi-Fi direct and so on whatsoever.
Okay, but in the absence of infrastructure, it's Wi-Fi direct that you use.
Yes, if you don't have an infrastructure, you use Wi-Fi direct.
Yeah.
Okay, next question.
Hi, you also talked a bit about receiving data that someone had already received from the wider internet but had a cached copy of. How do you plan to validate that that data is actually the same as the data that I mean, how are you going to validate signatures and all that sort of thing on the?
In this regard, we would we are relying actually on the functionality that the NDN platform provides, meaning that you can have some hashes that can be used.
Yeah, but if you don't have access to the internet, you can't validate the signatures that you would see there.
Sorry again?
I mean, if you don't have access to the network itself, then validating the signatures might be more difficult.
Well, this is another thing that we're working currently. We're trying to design a decentralized mechanism for providing public infrastructure that could work towards this direction. We haven't tackled this problem exactly, but this is interesting.
Okay, and one other thing, do you have any data to suggest how much of that, how often a request that you make actually is something that's similar enough in your social group that you would find the data local?
No, I don't think I have something like that now. We're having a field study which is more related to a scenario where we need some kind of services urgently. It's more of a distraction scenario in 3 weeks from now, 4 weeks from now. But it's a demonstration scenario, not actually, we're not using any kind of this.
Finally, for the record, I should have said I'm Alan Shalik.
Thank you. Right, so please announce who you are when you come up to the microphone, and please keep it really short because we have about a minute left.
Hi, this is Maysel Ladai from University of Essex. You talked about moving services to affected areas, or so I'm wondering, how do you discover affected areas or disconnected areas, and how fast you can move services?
Well, I guess that the discovery part would be somehow, yeah. What we're going to do in a demonstration scenario is that you can inform a user that identifies something. Could inform using this, again, some parts of what we have done.
Yeah, but that user is disconnected or affected. That he cannot tell you.
Be communications through an infrastructureless network, meaning device-to-device communications.
Right. So you're going to relay requests.
UAV that gets the data from that creates a Wi-Fi hotspot and can get the data from a user, maybe a photograph or something, and move it towards a centralized a civil service protection authority, and then this authority would be responsible for moving the service to the area.
Right. So basically a relaying approach.
Yeah.
Okay.
Are you looking at the security issues that comes with that?
So,
sorry, I'll be quick.
yeah, we're running out of time, but
We haven't looked so much into that, but this is something that we plan to do.
Okay, we'll talk offline more.
Yeah.
cool. All right. Sussex, meet Cambridge. Okay, so we're going to shut the line down now for that. The next speaker, thank you, Sotiris. Yay. Yes, is mesh networking. So this is the Picasso or mesh networking? Mesh networking. This is Menon. Okay, Menon, tell folks what you're going to be talking about. I'm going to pull you up.
Hi everyone, I'm Menon. I'm a research associate at Cambridge University. So this is a joint work with Polytechnic University of Catalonia in Barcelona, the GIFINet Community Network, and the RIDE project. Okay. So I'm just going to talk shortly in the next 5 minutes about our experience with the mesh networking. So this is QMP mesh network, which is kind of a subset of the GIFI community network located in the city of Barcelona. As many of you know, GIFI is the largest community network worldwide. So basically, QMP is an urban community network of GIFINet located in Barcelona. It has around 80 nodes distributed in the central location in the Sants district of Barcelona. And there are like 2-3 gateways that are connecting these users to the internet, right? We have a monitoring service which is running in the network, and we monitor the service for the last 5 months, and we try to find some patterns regarding different metrics, right? It's a production network. More than 200 people are using this network to connect to the internet, right? So here you can see some of the what we say outdoor routers, which users are using basically to build point-to-point links between them. You can see some NanoStation M5 and 3 devices. So our focus was to analyze the network from the local services perspective. So is it possible to run local services in this network? So we looked in 3 dimensions. One dimension was to analyze the topology of the network, then to see what is the node availability and the bandwidth distribution, right? So we started to analyze in the last 2 years the topology. So basically we wanted to know, does the topology follow some pattern? Like how does it grow, right? So it started with, in 2015 from this situation where we have like 30 nodes to a situation where we have like 80 nodes. So with time it became a fully meshed network. So we wanted to predict the growth, but we saw that the growth is unplanned, totally unpredictable in this mesh network, right? So yeah, it's a fully mesh network. It's becoming fully mesh network. The next thing that we wanted to see was the node availability. Basically, how are the nodes available or not? So basically, when I say availability, is the reachability of nodes. In our monitoring system, we saw that 25% of the nodes are less than 90% availability, less than 90% available. So this was one metric to include in our heuristics, right? And the most important thing was the bandwidth. We wanted to see what is the performance. Like, is it possible to run bandwidth-intensive services in this kind of network? So we characterized the bandwidth of the links for this 5 months period, and we saw that there is a highly skewed bandwidth distribution, right? 50% of the links in the network, they have less than 10 megabit per second, and the other 50 from 10 to 100 megabit per second. So what was the reason? So we got like an average of 21 megabit per second, which is rather good, right? I mean, it's rather even better than the Orange connectivity in Barcelona. So then we wanted to see the reason why this happened, this asymmetry, right? Because we measured the bandwidth in both directions, and we saw that 25% of the links in the network have a deviation higher than 40%. And why this happens? Why there is this asymmetry? We found out that some of the community network users are tweaking their devices. They are just increasing the transmission power, and they are changing totally the characteristics of the links, right? They are cheating in a way. So taking into account the dynamic topology, we have not reachable nodes and non-uniform resource distribution. So the question that we wanted to come is like, given this challenging environment, what is an effective and low complexity service placement solution? Like simple heuristic, not very complex, but that will improve the performance of the services running in the network, right? So we came with a HANET, with a BATS, which is like a bandwidth and availability aware service placement solution. Basically, it's a very simple heuristic. It runs in some phases. Basically, in the first phase, it partitions the networks by k-means, use the geolocation of the nodes to create cluster of nodes. Then we perform some bandwidth computation, like we try to find the bandwidth, the node with the maximum bandwidth in that cluster. And then we reshuffle cluster based on the network condition. And at the end, we have the orange color nodes, which are the nodes where the services are deployed, right? So this is the QMP deployment in Barcelona. We have like 80 nodes. Based on the outcome of the use heuristic, we went home by home to these community users, and we deployed Raspberry Pis in their homes. And now Addison is going to talk how we deploy our framework in these Raspberry Pis. Thank you.
Hi, good afternoon, everyone. My name is Addison, nurse in software. So I'm also from Cambridge, but not Cambridge Analytics. So can you click to my slide?
You have the clicker? I can do it.
Yeah.
And step up to the
Yeah,
mic
this-
and speak slower.
Yeah.
I'll tee them up. If you can speak a little slower, yeah.
So today I will talk about Picasso, which is like the ICN edge computing platform that we developed in Cambridge, which is also part of the mobile projects as well, as Sotilis already mentioned that. So okay, my slide is not coming. Yes. So I might keep talking then while waiting. So actually, this is a joint work with maintenance as well. So basically, what we try to do, like we try to understanding the characteristic of the computing network in Wi-Fi, and we try to define what is some kind of requirement that we should design the edge computing platform. Okay. My slide is coming. Okay, so as we see from the maintenance slide, like local services is going in community network, right? So it's some kind of the need that we need to provide the service close to the user as possible. So however, in looking to the platform that we have right now, we have like edge computing, which is mostly related to the data center environment, where they're using like a high server grade machine, and they use like a heavyweight virtual machine that and moving them, the service can moving them across the server, but still inside the data center. And also the facility that is quite good as well, like they have a very reliable electricity and also a high-speed internet or connection. However, look back to the what we have in the community network. We have a many limitation and constraint, like we have the limited bandwidth to access to internet, and then that's why it's going to be very difficult to provide the good services inside the community itself. That's why we come up with some idea that why not? We just try to move the service close to the user as possible. And thanks to the advancement of lightweight virtualization that I think you might know about, that like we have unique kernels or we have Dockers that allow us to make a services very small, and we can move them across with a little cost. And also, since it's small, we can try to overcome the intermittent connectivity of the community network as well. And this is some kind of overview of our implementation. So we call Picasso. And the service, as I mentioned, is based on the content, the Docker container base. And also we have what is important thing of Picasso is we implement the service controller. We can have the automatic decision how to decide that where and when you want to pay the services regarding many conditions like a network service, network condition, hardware resources, quality of service, and service level agreement. However, to support the decision making, we need to build the reliable monitoring systems as well, like how to collect the data in terms of the node usage, like available CPU or memory and so on, or network condition. And also one particular thing, important thing for the Picasso is different from another edge computing platform is about the smart forwarding. So in here, with the context of the mobile, we integrate the name data NDN, name data networking, and also delay tolerant network as well to overcome the challenge of the intermittent connectivity in community network and also the emergency situations as well. So this is the architecture of the Picasso. I might not go to detail for that because it's really complex, but we also submit the papers to the conference, but the paper should be available soon. And if you want to see, we can download the paper after that. So basically, as I mentioned, we have the service controller, which is a central entity. That we have the building the monitoring system to collect the data of the network connectivity, and also the hardware resources as well. And also we build an engine which is a modular design where the developer can upload or update the algorithm, how to select, how to deploy the services regarding that. And we have the local service repository where the service provider can upload that service image before distributed to the edge network. And also in terms of deployment, we developed the prototype by using Raspberry Pi as a service execution gateway, where you can plug that Raspberry Pi to your home router, and it's providing you environment to run the services locally. And the communication between the node here is based on NDN over IP. So I think I might not have time to go for that. There's just 1 minute left. So, but this is like the software architecture that we built. I might skip this one. And here, this is like last November, we went to Guifi with the help with the Leandros as well. So we try to deploy and test our system, how it's working. So as Menan also mentioned, that we have run some algorithm called bars to select what could be the critical node that we should deploy to cover all the area of the urban area of Barcelona. And this is the location. At the end, we end up we able to deploy 10 of the sec to across the Wi-Fi network. And then we run some experiment. So the first thing that we try to look into how can we improve the quality of service. So and here this is some result that we have, like we can improve the latency that the user can access the service faster. And also this is like the cost, and also looking to the network services as well, that how fast that you can deliver the services to the edge. So we compare our approach, Picasso, by comparing the classic IP unicast, and then we can see that Picasso reduce a lot of latency because we can benefit from the caching and name-based routing of NDN. And this is also another important thing. We are also measuring the traffic consumptions as well when we decide to deliver the services, right? How efficiency of the Picasso can reduce the traffic, and we can compare to the IP unicast, and that is some result. I might skip explanation for a while for this some. So, okay, at the end, so I would like to thank Professor Leandro and the Goodfeet people as well from UPC, because help us a lot in terms of deployment. Right now, the deployment is still running because the license that we deploy is still running, and then people, the community is still taking care of that and help us to monitoring. Yeah.
Hi, Ignacio Alvarez Amelin, Tech Fellow. May I ask for the previous presentation?
Okay, yeah.
And I would like to know how you measure the capacities. You say some nodes has 20 megabits, another 100. And I have a second question, but it's not
Basically,
really.
we were just simply by SSH to every of the routers of the antennas. We were just measuring with simple Linux commands the bandwidth of the links, right? So we were just collecting all this in a centralized repository and using that.
Then you are seeing each interface and count the bytes and so on. Okay, and you do that within
hours. So
yeah.
what we say, we have like captures.
Okay.
Only captures. So we go every hour collecting data. It's a production network, so we are careful to not cause overhead on the network.
Okay, and the transmission media is Wi-Fi.
Yes. Wi-Fi.
Okay, in
Most of the links are Wi-Fi.
5 gigahertz or 2 point? Okay.
Excellent, thank you. So again, one question each, so go ahead.
Hi, this is Maysan Nadar from University of Essex. Are you planning to make these traces available? So I'm asking.
Yes, these traces are available.
Okay, so we'll talk later about
definitely.
GitHub and pointers. Thank you.
Cool. And for those on the live stream, that was a question about the trace routes, yeah? Yeah.
Hi, Vasilis Chrysos from Sarantaporo Network. What kind of services did you deploy, and how did you decide that you wanted these services and not some other?
So the first thing was to analyze set of services in Giphy. We take all Giphy, like 34,000 nodes, their databases, and we just select the type of services that people use. The first service was distributed storage, as the most used service in the network, right? So this was, and we tried to find the open source version of distributed storage, like Tahoe Labs and these kind of things. Second was video streaming, because users in the mesh network, they like to stream like El Clasico games, for example, and we were trying to find to use like peer streaming from University of Trento as an open source streaming platform.
Thank you.
Excellent. Any other questions for Adesworn or Menan? No? Thank you both. This is,
I have 1 minute. I might
go for it. You have a minute?
So if you are planning to come to the next IETF, which is in Bangkok, so in November, so please, we also have organizing the conference
very
as
good.
well, SFN Tech. It's just right next to the IETF. So please consider to submit the paper or participate. Normally, the data for submission is in August, so we should have time. So please consider make your agenda for that. Thank you.
Excellent. That's cool. And for those of you that may know Dr. Kanchana, who Adesworn has worked with in the past, she has an interesting project, the Dumbo Network. Yeah, is that still running? Yeah. So if you go to the Thailand meeting, there's a great project where she's using mesh with elephants and others in the upper regions. Seriously. Okay, so next up is Vasilis Chrysos from Sarantaporo, Greece. We're pulling you up. Sorry, I'm not as organized as usual. There we go. Et voila. There you go. So tell them who you are.
Well, and now for something completely different. Actually, we're going to see the same things, but from a zoom-out perspective. Let's see about the social aspects of all this technology that you people here are building. So I'm going to talk about our network. It's a community network called Sarantaporo.gr, which is based in Greece. And I'm Vasilis Chrysos. Just a few words about me. so that you know who's speaking. I'm an engineer, a mechanical engineer actually. I am an entrepreneur. I'm an open data evangelist, and I'm a member and administrator of the Sarantaporo.gr community network. So Sarantaporo is a village in central Greece. It's next to Olympus Mountain, and you can see it over there. When we started our network in 2010, there were no telecommunication companies there, so people did not have an opportunity to access internet. So we are talking about a rural, isolated, mountainous area. A group of people stemming from Sarantaporo village decided that they wanted to change this, and they built the first mesh network in the village. It's a volunteers-driven endeavor. And soon after that, villages from all around Sarantaporo, from the area, wanted the same thing to happen for them as well. So they addressed this team and said, okay, could you come and build this network for us too? Soon, we had 15 villages in the area having their own mesh network offering open and free internet access connectivity. We have a non-profit organization. It was founded in 2013. Our vision is actually to create opportunities for people to stay in their birthplace, because Greek villages, as villages from all over the world, are being abandoned by young people, fleeing to urban centers because they don't have opportunities. So we would like to do something to change that. Our mission towards that vision is to eradicate the digital divide and provide local communities with equal opportunities to access digital economy and citizenship. So we are doing this by deploying and modern telecommunications infrastructure as a commons, and also training local people on how to use this technology, how to build it themselves, how to expand it, but also working on building a community around this infrastructure and around this project. So this is our Sarantaporo network in numbers. We have a backbone network, which consists of 24 backbone nodes connecting today 11 villages, 3 farms, and 1 camp, and 40 point-to-point connections. And we have 95 access points. These are access locations in the villages, and more than almost 50 active local community members. These are actual people living in the villages who are building and maintaining their own community network. These are people we work with in order to be able to run the network. I didn't say that our base is in Athens, which is 500 kilometers away from these villages, so we definitely need people there to work with. This is what we do. This is the antennas that we build.
Excuse me. Just a quick question on the previous slide,
Yes.
Julius Krobacek. What's the scale?
What's the scale?
Yeah.
Ah, yes, you're the one with
I'm
scale.
the one above scale.
Yeah, okay. So let's say that, I don't know if there's a laser here. Yeah. From here, which is Sarantaporo, to here, which is Larsa, is 60 kilometers. This
single
link
Wi-Fi
here,
link?
this is a Wi-Fi link. It's 60 kilometers. Yeah, this is the work we do. The mountain, you can see Olympus Mountain here, and this is Makis, who is putting up a mesh access point. Excuse me? Yep. No, it's Makis is his name. So this is a local associate we have in the village. This is how we work, actually. This is how we provide support to the locals. We have a map, we draw the position of the equipment, and we say here is a link that can be improved. You can see with orange color, and then people will go and set it up, and it will work fine. We provide training. Our main challenge is the distance and communication with local people, because as I said, it's a 500-kilometer distance from Athens. So we try to build communication channels. We have achieved that by using a popular application. So yeah, I don't want to do that. And that here too. Anyway, so our goal is to empower local people to build, maintain, and expand their own network. So we don't want to do it for themselves. We want them to be able to build it themselves. And we have been very thankful to be funded by Beyond the Net program of ISOC in order to achieve this for 2018 and 2019. And last Saturday, actually, we had this workshop in a village called Flamborough. We taught them how to make an Ethernet cable, how to change the IP settings in their computer. We're talking about people who are farmers, elder people. You will see them in the photo that comes next. So not very super techy stuff, but enough so that they can work with and troubleshoot their own network. So this is how a workshop looks like in those villages. You can see the people participating here. This is Yorgos explaining how a point-to-point link works. And this is Achilleas and Dimitris here, who are building the equipment so that they can also look at that, how it looks and how they can make it afterwards. As you can see here, most of the people are over 50 years old, and they are farmers. So one would wonder what's going on. Is it possible that these people will go and, build a community network, like make links and work with IPs and work with cables? And why would they want to do that in the first place, since many of them do not even use internet? Yeah, well, there's one very, very basic reason for that. In order to have their grandchildren visit them in the village, they have to have internet. If they don't have, the grandchildren won't come. So that's a very good motivation for them to be there and to learn how to do that and to do it well. We also have women participating. Here, these ladies building the cable. And actually, in this workshop, they were the first to successfully complete working network cable. And they said that, yeah, it was easy. It was like knitting. So for them, it's almost natural to do.
I love it.
This is how we show them about the network architecture, literally using satellite photos and having these tokens with the strings connected so they can visualize the actual network architecture. And then after we do that, we will go out on the field and start looking in various locations where we can actually put the equipment so that it works very well. Some best practice that we have learned throughout the years that we work, they need to have a daily support. And this is something that they cannot find with the incumbents. They shoot a question in our group. In the next few minutes, they get an answer. They need to have a personal contact, because we're talking that we're building a local community. We're not just building, putting technology in place. So it's all about building a group, building a team, being part of the same team. And we also do social events to facilitate interaction between the villages, because these villagers, it's not given that they will know each other or they will interact with each other just because they are in the same region. Many of these people did not used to know each other before, and now they are a group that is developing this network. This is how it looks, the support that we are providing. So they will ask here, what's happening here? Okay, then you can check this area, or you can check here and here. And this happens in real time. This is a regular day of communication with the community. We are trying to celebrate our success. Everything's green, everything's working fine. We're trying to provide support. We're trying to provide updates on the progress that we make so that everybody shares the community spirit. So Wi-Fi and internet connectivity are really, really important for these people. It has to have relevance with their everyday lives. So this is why I asked for the services before, because we cannot just go there and just deploy some services. We have to know what it is that these people can use and what it is that these people need. Is this my time?
No, you're fine.
Okay. For example, this is an agricultural community. They need tools for their everyday job. This is what we are trying to build with them. And something that very important. Learning about computer networking helps build awareness on privacy and personal data. In this workshop that I told you last Saturday, when we were explaining about how the controller, the access layer controller works, then one of the participants turns to another and said, "Oh shit, they're watching everything." And we said, "Yes, this is how internet works. This is the reality." Yeah, we also see that people, when they are supported and informed, they don't get frustrated, and this is really important in community networks. And they really feel proud to contribute and build. They feel it that their own infrastructure. Well, what happens after that? Well, this is the magic. There was a local riding club who asked to the incumbent, "I want to have internet connectivity," and they said, "Okay, you are off the grid. You have to pay 6,000 euros to bring you internet." And then they came to us and said, "Can you help us with that?" And with a few hundred euro, we expanded the network, and now they're part of our network. They have a very, very good connectivity. Our older members, our older community members help the newcomers, and now they're even organizing their own workshops without us intervening at all. So it's taking a life of its own, this community. They participate, yeah, the women, you saw them before. We are developing a farmer's log application through a European funded program, which is called Net Commons, which is really, really important for what they do. It can be a really important tool for these people. Yeah, Telegram application has helped us very much to keep in contact. We had a really important debate with these people about the data that they produce, and they somehow have built awareness on the value of this data and of who's managing and who's owning this data, which is a really, really big issue. We didn't expect that they will be so advanced in thinking about this stuff, but it came up, and we are very glad that it happened so. Yeah, and the latest news is that we have had, in the village, we have had a crowdfunding from people of the village to buy an access point for one of their fellow villagers who is disabled. They wanted to support him that way, and they bought it and put it in place. Yeah, well, this is enabling exciting stuff to happen in our region, in an area. Just imagine that the visiting doctors in the villages could not prescribe medicine because they couldn't have access to the online system. And now they can use our network to do so. That meant that people would have to travel 30 kilometers to the nearest city to get their medicine prescribed, right? We are enhancing social cohesion the way I told you before, so the grandparents have their grandchildren visiting them, and we are strengthening the citizenship by providing access to digital public services. We're organizing new workshops throughout the year. We're planning to share our know-how with some other community in some other place of Greece, because we believe that this is how it works with community networks. We are
Hello, can you hear me?
expanding access network.
Thank you. Vasilis, thank you very much for your presentation. Just a quick question with two parts.
Excellent. And
One, can you explain just very fast how the costs of
I don't
the
want to forget
network
Luis.
are covered?
Luis, we're
It
gonna see if
means
we can
how do
beam
you
you
pay
in.
for
So
connecting
just
to
one
the
second.
internet? And the second one is
Go
how do you
ahead.
manage the maintenance of the network? Since it looks like a large area, so how do you manage to keep all the network running? Is community-based that maintenance? Thank you.
Thank you, Luis, for the questions. Concerning our funding, we have various revenue streams. So one is through programs like funding programs of European unions. Another is through organizations such as ISOC that is helping us with some funds, but also local people, the node owners, as they are called. They are contributing a fixed amount of money, which is like 60 euro per year to cover for the maintenance costs. And the other pillar is that we do a lot of volunteering work. So everybody is volunteering here. We don't have any professionals working on that still. And the second part is that we have, let's say, hybrid model. The core team, as we call it, which is our organization, has an overview of the operation of the whole network. So it's a very centralized overview of if it works correctly, like through the controller. And then when we see that something is not working right, then we will contact the local team, the local group in the village, and ask them to go and intervene so that we can fix that. The other way is that they are complaining. So they're writing in the Telegram saying, yeah, my access point is only 10 megabyte per second, 10 megabit per second, so something's wrong. And then we will work with them and bring it up to speed. Yes, we have a unique, let's say, help here. We are connected to the local university of the nearest city, so they are providing us with the backhaul, and they are giving it as a social responsibility towards local villages, towards local community, towards people who cannot access internet otherwise.
Okay, and in the queue, Addison?
Yeah, actually, my question is related to the first question of Luis, but I might ask a bit more further, like about in terms of sustainability. You say that now you're subsidized internet connection, right, to the village. So, and also the villagers also sharing some costs as well, right? So my question is, what about the long term? For example, like if some villager decided to quit from the member, and you might lose some of the user who pay, right? So what is your idea about how to?
Yeah, so this is something that we are currently working on. We haven't solved the business, let's say the social business model question yet, but it's an ongoing process. We believe that the more you engage the local community, the more they will support it. So now we are receiving support from many people. Everyone who has an access node in his house will contribute with a steady amount of money each year. We also do fests, local fests, and we gather some contributions from there as well. We try to diversify our revenue stream as much as possible so that we minimize the risk, but we cannot say that we have solved the sustainability problem yet.
Okay. Thank you. Yeah.
Hi, Rich Thanky from Jangala. Just a question about your workshop and how you were teaching people about the basics of network building and basic concepts. So two questions both linked to each other. One is, what were the areas that people had greatest difficulty with, say IP addressing or whatever? And secondly, how close are you to, I mean, how has your model been replicated by nearby communities and other similar communities? And you know, getting these skills to spread is the important question to make something kind of that can grow quickly. So how close are you to that?
Okay. Concerning the first question, things that they cannot see, like they cannot visualize, they cannot comprehend, because these are people who are not experts on technology. So they find it quite difficult to understand, for example, the network architecture, the backbone layer, the access layer. These are things that confuse them. So that's why we try to visualize it with the map and the tokens. And yeah, if you go deeper into more advanced networking concepts, then we lose them there. It's really, really difficult to work with that. And this takes time to build. But let's say 90% of the problems that our network has can be solved with basic knowledge on how to make a cable or how to align the links, or how to put it in the right position in the right way. The second question was, how to replicate what we do. It's really, really important for us to, let's say, package our knowledge and experience and, let's say, export it or transfer it to other areas. It hasn't happened yet, and it's really important for us that this summer, it will be the first time that we will go to another village along with people from our villages and stay there for 3 days, do the workshops, build the first node with them, and try to teach them how to do it themselves. But it's really important that you create connections, so that after you're gone, after you leave, they don't feel that they are on their own. They have to feel that we are there to support them, and this is how they will continue growing.
Where can we follow your progress this summer with your replication? Do you have stuff on your website? How can we follow your?
Our website, unfortunately, is in Greek, and we are really trying very hard to build
The
out.
Gaia list, you could let us know.
But definitely, we could do that through the Gaia list, or perhaps we will make a, let's say, Medium blog, or I don't know.
Thank you.
That's a great question, though. Thank you, Richard. Okay, we have about a minute for a question and a minute for an answer, because we got 2 more speakers.
Yeah, I'll be super fast because I think my question overlaps a bit with that one. I was curious about the engagement you get from that large bunch of people over time. Do you find that maybe after a couple of years or less, you become very highly dependent on 1 or 2 very engaged participants? And in that case, does kind of the single point of failure move away from being the infrastructure and towards the individuals? And if that happens to be someone who leaves or, God forbid, dies, does everything fall to pieces?
We are here where we are today after many years of intervention in the region. So we have worked with many people. People actually have come and have gone. We renew the human resources that we have, and we see that in each village there is always 1 or at most 2 champions. The people who are most, let's say, militant, and they will go and build everything and move and inspire other people to do so. These are not, let's say, unique people. I mean, if somebody leaves, then somebody else will eventually take his place. Not very soon, but there will be somebody. And it takes a lot of effort from our side to be there and to continue building the community. And this is not something that you can, let's say, secure for 100%, because what we do is 90% social and perhaps 10% technical. So you have always human relations to work with.
Cool, thanks.
Thank you very much. This sounds like IXPs in the making as well. Yeah, 80%
Definitely.
human, 20% technical sometimes. Thank you, Vasilis. That was great. Thank you. Next up is Muhammad with the Community CellNet. Oops, no. Yeah, that's okay. So please welcome Mohammed Qassam from Edinburgh. Yeah?
Hi, I'm Mohammed. It's kind of, voice is fine, or I need to hire? Hello? Yeah.
There you go.
So I'm Mohammed Qassam from University of Edinburgh, working a PhD student working with Mahesh Marina. So today I'm talking about our recent studies about using TV white space as a backhaul for a cellular network over some deployment in Highland in Scotland. So as we already know that almost 52% of the population worldwide doesn't have internet connection, which is more than 50%, more than half of the population worldwide. But this wouldn't be very weird if we know that 40% of population worldwide are still living in rural area, and the most contribution are coming from Africa and from South Asia. So it's more, these figures are more related to each other, meaning that this 50% that offline people are, most of them are likely living at the rural area. So why providing connectivity for people in rural area are challenging? It's mainly for two main reasons. So the first reason is the infrastructure cost. So from the operator perspective, it's not very economical. There is no any gain from providing deploying a very high cost infrastructure when I will gain very minimum revenue or something that cover the cost. So this dilemma between how much I pay and then how much I get back, meaning that preventing the actual operator from doing this deployment. So, but why there is no much revenue in this area? It's mainly for two reasons. First reason that either the people in this area are very sparse, are not really, maybe you find one or two houses distance between them like 1 kilometer or something, or either they are low income people living there. So this leads us to the second problem, which is affordability. So if the people living in a rural area has a low income, then asking them to paying a very high monthly subscription for the internet connectivity is not very helpful. So we thought that these are the two main reasons that prevent actual commercial operator from going to the rural area to develop to deploy a cellular network there. So, but this problem is not only a problem of developing countries. It's still a problem of also the developed country. Here's a figure from Ofcom, the Office of Communication in UK. It's showing that only 2% of premises in UK they can have only 10 megabit per less than 10 megabit per second broadband speed. So the problem is not just a problem of developing countries. It's still major areas and rural areas worldwide facing this problem of low speed or non-connectivity. So how is that related to 5G? So recently, 5G has some objective for what we called a 5G era, which is 2020. So one of these objectives is to provide something called universal access, or to connect the remaining unconnected people, the 50%. So there's a lot of effort from both industry and research, and different solutions have been proposed, including for example leveraging the lower frequency like a TV band frequencies, or using drones like a mobile base station that can be moving from for a rural area connectivity, and more of that. Some recent work from Facebook and Eurocom team that they do this open cellular software defined platform or open air interface from Eurocom. It's very familiar. It's very recently become very known in the community of research community and industry, that they provide like an access side, but it's software defined that you can easily deploy over the platform, like USRBs, this type of software defined platforms. So, but what is missing now? So, in this work, we propose a redesign for this rural cellular connectivity. We thought that these design principles are not yet recovered in the community, in both community. So first thing, simplicity. So because it's a community-based infrastructure, so we need simplicity. We need something plug and play that the community themselves they can go and plug the device. I mean the access device, which could be either a router or could be a base station, small base station, and that's it. And then everything is work fine. Second thing, scalability. So how we can scale this up? So if we start by 10 users, how we can does this is scalable? Can we go for 40, 400? but not just the scalability in terms of the number of users, but also in terms of the services I can provide. So if I can start for example by 10 megabit per second speed, can I go for 100? So this is the scalability we mean when we're talking about the scalability in this model. The third thing is applicability for new services. So I will talk about this in more details in the coming slides. Fourth is cost efficient. For sure that we need because the whole objective of this that we cannot have a commercial operator operating in this area. So we need something cost efficient. Something can be deployed with a minimum amount of cost. So and the last thing is availability. So I mean by that is the ability of this community networking or network infrastructure to communicate with existing other community network or existing commercial network. Like maybe can I call from for example if I'm using my commercial network in an area like 100 kilometers and 100 kilometers, if I go away from this area, can I still use my community network? So this is how we talk about adaptability. So because we don't have too much time about that, so we talk about the third point, which is providing high broadband speed, in the next couple of slides. So, but general, as a high-level architecture about this deployment model we did in Highland, we have the three main components. First component is the access point or the access network site, which is closer to the users, which is a normal could either be an LTE-based station, which is commercially available, or one of these software-defined platform, which is open air interface or open cellular. The second part is TV Watt space backhauling link from the location that to provide, which is carry the traffic of the access point or the access network to the internet. The third part, which is the core, because it's a cellular network, so we need a core part. Core part meaning MME and APC, which is we implemented by cooperation with Microsoft as a core in the cloud. But also because there is not a lot of time, but a lot of details are in our paper. So I will focus only on the TV Watt space backhauling link. So before we went to the field, we do some analysis using a SPLAT software, which is a software that used for a connectivity for availability analysis, and it considers the terrain and the shape and the weather and these type of things. So we select an area in Highland in Scotland, which is an area at like 60 kilometers times 60 kilometers, and we do our analysis in this area. So we mainly focus on two questions. The first one is how many usable channels are there. By talking about usable channels, it's different than available channel. I will define the difference between usability and availability in the next slide. And then the second question is how the spectrum is distributed. Is it available contiguously or fragmented into different fragments? So starting by the first question, which is TV Watt space usability. So in recent study over the last 10 years, the whole term commonly used in the literature is TV Watt space availability. Availability meaning how many channels are there, and there is a lot of models. Either it's by using sensing techniques or by using geolocation database that ask the TV Watt space device to query the database, and then the database by where it sent its location, and then the database reply by list of available channel. But this is the TV Watt space availability. But this list of available channel, it's actually over optimistic. It's unrealistic, because in some situation I could have like the whole available channel, 40 channel are available. The database said that, but when I'm trying to use them to deploy actual middle mile or backhauling link between two points, I'm facing a problem of severe interference at the receiver side. Why this has happened? Because the receiver side, which is a TV Watt space receiver, it's suffering from different interference coming from different primary TV transmitter, and which means that the SNR level at this receiver is very low, which make the connection with a TVOT space transmitter is not possible. So the main difference between TVOT space usability and TVOT space availability is how much it's about the quality rather than the quantity. So the channel, if the channel is X, has a SNR above some threshold, which if it is true, then this channel is usable. If it is not, then this channel is non-usable. So this is the main difference between TVOT space availability and TVOT space usability. Availability is using the quantity side, how many are there, but usability are using the quality, how many can be used actually for this link communication. So for this, we have here some results from our analysis. So the graph shows the difference between what is reported from the TVOT space geolocation database. We use a commercial database called First Spectrum, from First Spectrum. And then we did some analysis about either these channels are actually usable or not. By usable, I mean we measure the SNR level on these channels, and by different threshold, so 5 dB and 10 dB and 20 dB, we can see that for a median, for 50% of the location, the difference between the two terms, usability and availability, is around 200 megahertz. So, for example, the database reporting that there is a 30%, 30 channels are available, but the actual usable channel are just 5. This is for 50% of the location. For a second set of experiment, set of analysis we did, it shows it's a spectrum fragmentation. So we now know that the spectrum is available, but because it's the TV channel is just 8 megahertz, and to achieve high capacity link between 2 points, like you need to aggregate some spectrum, right? So I mean the 8 megahertz is not sufficient. You need to have like 20 megahertz, 40 megahertz, 60 megahertz. So you need to know, is that channel, the frequency is available contiguously or fragmented. So we did this study to figure out what is the nature of the spectrum there, and we found that the spectrum is still fragmented. Yeah, we could have 20 channels are available, but they are not available in one chunk. They are separated by some non-free channels. And we found that for a 50% or the median of these of this spectrum, there is the fragment size. The fragment is around 8 fragments. Here, by 8 fragments, I mean if I have 200 megahertz, I have 10, then plus 10, plus 10, plus 10, and they are not contiguously. They are fragmented. So last thing, we did very recently initial deployment using this by this model. We have a base TVOT space and a client TVOT space using the Adaptron TVOT space devices for over. It's 1 kilo. It's 1 kilometers. Yeah, just very.
Julius Krobachek, that was my question.
Yeah, it's still. So the idea of this deployment is not about the distance. The distance is important, but the idea is to achieve the high capacity link, that we can go from 8 megahertz channel until up to 80 megahertz channel. So we started. This is a very recent deployment. We started by 8 megahertz channel. Here at the base TVOT space, we have the internet cabinet, which has a fiber connectivity, and then we have here with the client TVOT space, which is in this area there's no any connectivity, and this is the backhaul link. Also here we have LTE base station, small base station, that provides cellular connectivity for a 4G mobile network in the surrounding area. So this is a very recent, and it's just an initial deployment. Our objective is to make this link over like I said, 80 megahertz channel, not just 8, and then to scale up the number of users that we can serve by the LTE base station in this area. And this concludes my talks. Thank you very much.
You were fabulous. Excellent. Any questions from Mohammed? Yes.
Hello, Mohammed. Here, Andres from Cambridge. Very nice presentation. Really good results, I think.
Thank you.
So I got a couple of questions. So the first one is, in databases, models most of the time overestimate the occupation of the channels in the areas in which the primary users are deployed. How would you explain that you're finding this counterintuitive result?
Okay, so for that, okay.
Yeah, I get another question, but based on this first one, yeah.
So basically, the database is focused from the transmitter perspective. So the transmitter sends its location to the database, and then the database supplied by a list of available channels. But in our analysis, we focus on the receiver side, which is not part of this communication with the database. So we're saying that if I choose, for example, if I choose channel X and let the primary the T-Watt space transmitter to transmit by this channel, at the receiver side, it might be that the case that this channel will be very interfered. Why? Because maybe this receiver location is in intersection location with different primary transmitter, TV transmitter, which make the interference are very high on this channel. That's how we find that we have a set of analysis that we found that in different locations that there's a huge gap between the availability TV space and usability.
Yeah. Have you experimented with transport protocols, TCP? Actually, the equipment you're using, I assume, is using 100-222 standard.
Yeah, it's the very commercially standard. Yeah.
Have you performed some TCP measurements? And stuff?
No, we're focusing mainly on physical layer and MAC layer.
All right, so I strongly recommend you to do that. You might find surprises.
Yeah,
in the best of class of service. Right.
Yeah,
that's it.
very
Thank you.
Thank you very much.
Addison, okay.
Hi, I have a question about the 5G because you mentioned in your title is about 5G, right? So how it related to the TY space? Or it gonna be like a 5G for developing region or something? Using
okay, so 5G context here is just so 5G has a promise of having a very high gigabit per second speed and low latency.
Yeah,
and that's how this related to what we are doing. Now we are in this rural area. We're using 4G cellular commercial devices, and then we have this capacity, this link, which is 8 megahertz. So to provide a high bandwidth for these people in this area, so we need to aggregate multiple. The bottleneck is in the backhauling link.
Mm-hmm.
So we need to aggregate multiple TV channel. So from here, there's a link between what 5G proposed with having a high-speed broadband and what we are trying to achieve. We are trying to solve the bottleneck at the backhauling link to aggregate multiple spectrum that we can achieve the throughput that 5G promised was.
Okay. So maybe one question: are you working with the regulators or something like that?
Sorry,
regulators like Ofcom or something that do what is their views about the TY space or 5G? Is there any chance to provide you some license to run the 5Gs in
So as far as I know now, Ofcom they're trying to sell the 700 megahertz band.
Yeah.
But I'm not very aware about what's their view about this. Yeah.
As I heard so far, like Ofcom, they want to use 700 for something else, right? But you still have 600 megahertz for running.
Yeah,
TY
from
space.
400 to 694 something.
One last question: the base station they're using is from IP access.
Yeah, IP access,
Okay,
exactly.
thank
Yeah,
you.
yeah, exactly.
Excellent. And 1 minute. Just let's go as quickly as we can. A minute.
So a really interesting presentation. Quick question. The high bandwidths that you need, are you talking about point-to-point bandwidth?
Yeah.
So 5G seems almost a bit redundant here, since you have point-to-point technologies that can do. I mean, for example, even in 5 gigahertz at the moment, 60 gigahertz, 24 gigahertz in many parts of the world, you have low-cost commodity equipment based on, available in unlicensed, exempt, and licensed bands that can achieve the kind of speeds that you need. I mean, I think in 5 gig you can get up to a gigabit per second, and in 60 gigahertz and 24 gig you can get even higher.
Yeah, that's true. But the idea of using DVAT space here is just because it can also propagate for a longer distance.
Right.
So if you can achieve the same amount of broadband or throughput that the actual commercial device that you mentioned that it's achieved now, but over a longer distance, this is the.
So I'm failing to see the relevance of 5G here. So, reaching that kind, having that kind of propagation with 5G would need similar kinds of spectrum. So, you would need, a 20, 40, 60 megahertz chunk of sub 1 gigahertz spectrum.
Yeah.
Now that is, precious, valuable stuff that is being snapped up by mobile operators kind of worldwide. But if that was available, then you could use any technology in there to achieve that kind of throughput. 5G does not necessarily let you break Shannon's law or do miracles, really, does it?
I see, yeah. But mainly because we provide here, it's not like, it's mainly solar connectivity. That's why we mentioned 5G in this context. So it is not just a data, it also, our next focus will be on also the voice. Just also providing a voice for this community, not just the data.
Okay.
So that's why. Yeah. Okay. Yes. Totally.
Thank you for the questions and thank you for the presentation. Excellent job. Good job. And next up is John Brewer from NSRC. And if someone has the blue sheets, please circulate them. We'd like for you to sign in if you're here for Gaia. Who has the blue sheets? Wave them around. Got them? No? Yes? Somebody? Awesome. Can you just recirculate them? Yep. Thank you.
Okay, so 30 or 45 seconds of background here. I founded and built a national wholesale wireless access provider in New Zealand starting in 2003 and sold that company in early 2011. 400 point-to-point links, about 10 gigabits per second of licensed capacity, another 10 of unlicensed capacity. So I've done a lot of this stuff from the commercial perspective. We did use a lot of open source technologies, Linux routers, BGP, OSPF, a lot of that stuff. So I love what's happening in the community network space. And in fact, I was inspired by MIT's RoofNet to start my business way back then. Last 7 years, though, I've been a consultant to network operators, to governments, to commercial organizations, and I do a bit of training for Network Startup Resource Center, who send me places to teach network engineering, wireless engineering, and IoT. These slides were developed for an IoT workshop that I give for NSRC, and I'm just going to take you through a couple of protocols because I know people want to start adding IoT to their community networks. So first off, IoT protocols exist because we have device constraints. We've got low power, we've got low CPU, we've got tiny devices, and we have network constraints because IoT devices do not have big antennas put on them. You don't put a dish antenna on an IoT device. You don't put it on the roof so you get clear line of sight. You got radio power utilization because a lot of times you want these things to operate on a battery or a small solar panel. You have interference from yourself, you have interference from other devices, and you have these ideas that you might want to have itinerant connectivity or mobility of this device. You might want to take your sensor and move it from one place to another. These are not things you do with an antenna that you stick on a rooftop. So, unfortunately, fortunately, Wi-Fi is the most popular IoT protocol out there. The Internet of Things really is built on Wi-Fi today. What's crazy about this is you can get a Wi-Fi module and a microprocessor on a system board with an operating system and have a usable device for $7. And that's buying one at a time. Once you start buying 1,000 of them, you get it down to $3. If you buy 10,000, it's probably $2, so on and so forth. So Wi-Fi is like the default protocol for connected devices, and it works well where there's power and Wi-Fi coverage. But doing secure mobility with Wi-Fi is quite hard. A lot of people, when they talk about moving Wi-Fi sensors around, say, oh, I'll just latch onto an unlicensed network. Richard Lamb, formerly of ICANN, had a little device that he would find open Wi-Fi networks and infiltrate them. That was cute, Richard. Anyway, Wi-Fi does not solve all the IoT problems. Most of all because it's not designed for battery consumption, but the great thing about Wi-Fi is that anybody can run a Wi-Fi network, and you'll find with IoT this is not the case. So we have got the IEEE 802.15 for whatever series of protocols, which include Zigbee, Bluetooth Low Energy, 6LoWPAN. I've gone to 2 different research groups and working groups this week about 6LoWPAN. Frequencies, 868 megahertz, 915, 2.4. You know, we were just talking about TV white space a few minutes ago, and we're talking about TV white space because the frequencies are lower than 2.4 gigs. They propagate better through trees, through difficult environments. So getting your devices on UHF frequencies, low frequencies like 868, 915, means they're going to have a lot better performance than 2.4 gig. You may have anywhere from 20 kilobits per second to a megabit per second of traffic coming out of your IoT devices. IoT devices I work with are like kilobits per second at the most, and that's like a couple of times an hour. Anyway, you get star topologies, trees, meshes. If you're really interested in that, go to the working groups. Low power consumption. You can have battery-operated 6LoWPAN devices that may last a couple of years if you're careful with the power management. They can be low cost if they're in the 2.4 gig band. 802.15 devices in 868, 915 are definitely not low cost because there's no economics of scale there. People just don't make enough of them for them to be cheap. But 2.4 gig, everything's cheap. So there is encryption, 128-bit keys. It is a personal or local area solution without any real options for mobility. If you build a 6LoWPAN network or you build a Zigbee network or a Bluetooth, whatever, it's going to be for a small area, and it's not going to be a network you're going to build across a number of communities and share resources. You've just got a bunch of little islands. But a great thing about this is anybody can run an 802.15 network. Anybody. Okay, we have some really bad stuff. Like if you buy, if you go to the toy store and you buy an IoT device, or you buy it off AliExpress or Amazon or whatever, you've got a weather station. I hate weather stations. Cheap weather stations do things like run unencrypted serial across 433 or 868 megahertz or 915. Some people take advantage of this by having fun and capturing the information and making it useful. Some people take advantage of it by making a garage door opener that they stick on the roof of their car, and they drive down the street and they open everybody's garage as they drive by. A colleague of mine gave a talk at a hacker conference about how he did this in New Zealand. That's because things like Lo-Fi and Motino, based on the RFM69W chip, which is like pennies for the chip, very, very insecure in most cases. But it is very inexpensive. If you want to buy one of these and play with a module with a CPU and the wireless, $3.50 for like one. Yeah, pennies if you're buying 10,000 or 100,000 of them. This doesn't scale beyond local applications. Yeah, I guess anybody can do this. Please don't. Just don't. Sigfox. Is there anybody from Sigfox here in this room? Because there have been Sigfox people in the research and working groups that I've attended this week. Sigfox is crazy because they're an IoT company that owns the whole stack. They own and operate the receiver network. They own the protocol. They own everything about it. They've been very successful in infiltrating local governments and utilities in selling their, accessing, working with. I didn't mean infiltrating, really. They have a cool device that has very low power consumption. It was designed for battery operation. Its limitations are you only get 140 messages a day, and they're 12 bytes, so you don't have a lot of data capacity. Works out to 10 to 1,000 bits per second. Look, that's great if you're a water meter or a power meter or an anemometer or something that has, you really only need to talk 140 times a day or 5 times a day. That's great. You can do payload encryption. It is possible to have mobility. So like you can roam a Sigfox device within Europe because it's all 868 megahertz. You can roam a 915 megahertz device between American countries in the North America, possibly other countries that have 915 like Australia. And the thing about Sigfox is that only Sigfox can run a Sigfox network. If you want to run a Sigfox network, you become a partner. They lease you the base station. You put it up on your tower. Communities do this. Small wireless operators do this. But it's not yours. We got another one here called Weightless, and Weightless is funny because it was designed as an IoT protocol for TV white space. And I got involved with Waitlist in 2012, and they just had this beautiful protocol to do very low power, battery operated. They just built a gorgeous protocol. And then they were really constrained because only one company was making the chips, this company called Newell. And in 2014, Newell sold themselves to Huawei. And then Huawei took the intellectual property and sort of shoehorned that into NB-IoT, which is now a 3GPP standard, and a lot of people call it 5G. I think technically it will come out in a release before 5G, but people are calling it 5G. It's a really nice protocol. Battery-powered nodes, they can sleep for days, and the base station will keep track of the fact that these nodes are going to wake up in like 3 days and want to talk at a particular time. You can go from bits per second of traffic to megabits per second, so you've got this whole adaptive modulation regime for what you need. Public key encryption, mobility scaling to international networks. Mobile network operators will be running, if they're not already, will be running NB-IoT on their existing base stations and existing antennas just by adding a software load to their base stations, because NB-IoT will run in channels the same size as GSM or GPRS channels that they've just retired. So you may have a cellular operator running a 900 megahertz 3G network, and in the padding at the side of the carriers, they'll be running some NB-IoT carriers. But the problem with NB-IoT is that only mobile network operators can run it. Now, Waitlist does have a narrowband option that technically you could run as a network if you could find somebody to make and sell you the hardware. And I keep looking for hardware, and I haven't found any yet. So that's kind of a not yet type thing. We've got another cellular thing that's also referred to as 5G. Yeah, 5G is everything. Everything is 5G. LTE machine type communications, Cat M1 or Cat 1M, however you want to say it, uses existing LTE base stations, and there's 6 230 kilohertz channels. So this is narrowband, but not like super narrowband. So you get 6 channels per 1.4 megahertz carrier, which allows cellular operators to say, take their 20 megahertz of LTE spectrum and maybe portion off 1.4 meg on each side and run some LTE services on the side of their big fat broadband LTE carriers. The endpoints, like the terminal units, they decide how often they want to talk. Of course, it's cellular, so the mobility scales to international networks. This is like SIM card based stuff. And since it's that way, only a mobile network operator can run Cat M1. 2 minutes. I can do this. I'm almost in the last slide. I am on the second to last slide. LoRaWAN, low power wide area network. Nothing to do with LoRaWAN was invented here at IETF or at IEEE or anything like that. But LoRaWAN was designed for battery-powered wireless devices, supports bidirectional communications, mobility, localization. It is a star topology. It does not mesh. Mesh is, I'm not a big supporter of mesh because when you mesh, you've got to have nodes that are on and listening all the time, and listening is quite a hard thing for IoT devices to do on battery power because you've got to run your CPU, you've got to demodulate signals, you've got to say, hey, is this for me? Do I need to do something with it? Whereas star topology, your end device on the battery says, hey, I want to talk, I'm going to talk, and I'm going to go back to sleep until I want to talk again. So 0.3 to 50 kilobits per second via adaptive data rates. We set everything to 0.3 kilobits per second in Kathmandu 3 weeks ago when we ran a workshop and did a LoRaWAN deployment because we just wanted it to work. There are multiple levels of encryption. It's really cool. I'm actually the operator of a LoRaWAN network in New Zealand and Cook Islands and now some base stations in Indonesia. As the network operator, I can never see application payloads because the application data has a second encryption key. So I can see the metadata about the packets going over the networks that I operate, and I never have any idea what's inside the packets. LoRaWAN can scale to international networks. Anyone can run a LoRaWAN network, and that's where we get to the community part because we have this wonderful thing. Oh no, I've got 2 more slides, sorry. Okay, if you have a community network and you want IoT, you can use 6LoWPAN, but it's a personal area network. LoRaWAN is probably the best for large areas, and we have this group called the Things Network based out of the Netherlands, I think. Thank you. Who have done this amazing thing because they have provided a LoRaWAN controller. The way LoRaWAN works, you've got end devices, you've got base stations, and the base stations talk to a controller, and the controller is like a mobile network core. It kind of orchestrates the movements of packets to and from. TTN is a free cloud controller for community IoT networks. At the moment, there are 3,317 as of whenever I took this screenshot yesterday or the day before, gateways online. And if you make an application on TTN, like I make it here, anyone can join that application on any TTN-enabled network, and it will just work. So if you want to do a community network, my recommendation is LoRaWAN and TTN, but you could do Wi-Fi, you could do whatever. Sorry for going over time, Jane. I get excited about these things.
We do too. We love it. It's okay.
Question me.
Are you done?
I'm done.
Oh, wow. Right on time. We've got about 2 minutes for question and answer because TikTok's coming in.
Okay,
John,
this
you're
is
up.
informational. I posted on Gaia mail list, but there's a cool measurement of IoT homes in UK. There's a paper on Archive you can see in the link I sent, which is pretty alarming in terms of the amount of data most practical systems people are buying in developed regions generate, which is very scary. Second thing is, if you run a LoRa network, we have one for air quality and transport monitoring in Cambridge, where we then brought some nodes to London. You discover you're not alone. This stuff works really, really well. Like you said, it's a really nice thing for low bit rate, long range. But then you discover everyone else has discovered it because you can get USB dongles and build a Raspberry Pi based thing, tomorrow or today or last week. So I think we found 12 in London last year. And there's an issue with coexistence of multiple radios. So this came up in one of the folks visiting the thing, and there was a side meeting about what do we do about all the different types of radio for IoT that are low bandwidth, but are living in the ISM band. And the band is getting crowded by different protocols that don't know how to coexist nicely. And it's not just being underlay and overlay because there's N of them, not 2 of them. So it's a really hard problem. It's sort of generalization N squared worse than white spaces. And I think somebody needs to do IETF scale thinking about how we do the coexistence. I don't think it's an issue for the capacity. I think it's just a coordination issue.
Sure thing. And my only counter is that I believe that chirp spread spectrum is indestructible. And if you have a sensitive enough receiver, you can listen to multiple interfering transmissions and pick out the right one. But that's just my professional experience in it. In a much smaller place than London, okay? I have not seen the type of interference that you have in London yet. And so it could well be an issue that we need to think about.
So really fast questions, fast answers. We've got about 2 more minutes. The TikTok folks are here. They probably want to get in the room. So, Dimitris.
Ignacio. I would like to ask about, because some of the types of IoT are not really open. I would like just you mark which are open and which are not.
Okay, so LoRaWAN is an open network stack. However, the LoRa radio protocol is not open because there's only one manufacturer of the chip, which is Semtech. Cat M1, I guess it's open in that it's 3GPP, but there's a lot of intellectual property encumbrance, and you do have to get license fees for that. Again, NB-IoT. Waitlist, probably technically no, maybe is mostly open, but I think there's IP and licensing to do with that. Sigfox, of course, is completely proprietary. These things are pretty much open, but they're rubbish. 802.15 protocols, I mean, yes, they're open. You're going to be paying licensing fees bundled into the chips because some people have IP around them. Deep down inside, there are some things that are not open, but they're pretty open. Pretty open.
Okay, and John's here for the rest of the day too. Go for it. Last question.
Dr. Stimling to Hamburg, just about the coexistence. I remark there is a draft in the T2TRG group about exactly that. So in case you're interested in discussing that further, maybe you'll want to go there.
Thank you very much. And we had a question from far afield in Mexico, which is going to be typed into the chat, which it's regarding security. Can you comment how secure your proposal is? Rather the infrastructure. We
My-
might take this to the Gaia list. Yeah.
Okay. My own infrastructure, the base stations are IP backhauled, but they don't have a default route. They talk on a private network. They only know about a proxy server that gets their traffic to the gateway, to the network controller. So I'm pretty happy with the security. And of course, all of the over-the-air stuff is incredibly secure. Other protocols, yeah, not so much in some cases.
And gracias from Mexico answered the question.
All right, thank you.
Thank you very much. We're going to take this to the Gaia list. Huge thanks to everyone that kept to time. It was amazing. And we're going to scoot so the TikTok folks can come in. But thank you, thank you. And stay tuned because Leandro and I are going to probably do what?
How you doing?
Okay. We're going to work on an info doc. So in any event, for those of you leaving, excellent. For those of you that will play on the list, we'll see you later. Thank you.
I use low IoT out of Switzerland for our network controller. So I know they're. No.
How are you?